It's an extraordinary privilege to be here and be able to talk to you. So thank you to the LMS and to ICMU, the wonderful work they're doing here. I'm going to, so normally lecture courses sort of build gradually one thing on top of the other. This is be a bit different. I'm going to cover many different topics, from number theory, a bit of physics, as Masha mentioned, some combinatorics, some graph theory. But I want to emphasize is how everything is very interconnected. So I want to emphasize the connections between subjects, which is really striking in the subjects I'll talk about. And if you choose to come to my lecture on Monday, many of the different topics appearing here will all somehow come together, hopefully, next week. So the first topic, should I put this? No. This is the, okay. Okay, so the first lecture will be about number theory. So it'll be about the values of the Riemann zeta function. Irrationality, and a little bit about P recurrences. And I'm going to begin with a historical introduction to many of these ideas. And the problem I first want to talk about is famously known as the Basel problem, which is the beginning of much of this story. So I'm not completely sure, but so Wikipedia says that the following fact was known in the 14th century. I'm not completely sure, but certainly the Bernoulli brothers knew this, and that's that the sum of the reciprocals of all integers is infinite. So certainly it's been known for a very, very long time. And from this, it's natural to ask variations of this question, and indeed Mengoli in 1644 asked the question, what happens if we put the sum of the squares of integers? So this is 1 plus 1 over 4 plus 1 over 9. What's this? So this problem remained open for a very long time, and it was solved by Euler in 1734. And he immediately became extremely famous. And it's called the Basel problem because Euler was from Basel. So what did he show? Let us define, can you see if I write down? Can you see? Yeah. So define zeta of n, so zeta for sum, so for an S, equals k bigger than or equal to 1 over k to the n. And this converges when n is equal to 2. So I will take n an integer. So these numbers were very, very well studied far before Riemann's time. It's only Riemann who considered n as a function. So it's now called the Riemann zeta function, but of course this was studied much, much before that. So Euler showed, what he proved is that zeta 2 is pi squared over 6, zeta 4, so that solves the Basel problem, Mengoli's question. This sum is equal to pi squared over 6. But at the same time, he proved a lot more, and he proved that zeta 4 is pi 4 over 90, and zeta 6 equals pi to the 6 over 945. And in fact, his proof gave a formula for every even zeta value. So sums over even powers of all integers. And so the answer is expressed in terms of Bernoulli numbers. So we define x over e to the x minus 1. N factorial. So the coefficients Bn are certain rational numbers. And if you expand this, you see that B0 equals 1. B1 is exceptional because in general all the odd Bn's for odd n vanish, apart from this one. B2 is 1 over 6, B3 is 0, B4 is minus, etc. And so Euler's formula, so Euler's theorem, is that zeta of 2n equals minus 1/2 2 pi I to the 2n over 2n factorial B2n. So normally this formula is written a bit differently, but if you think about it, it's going to be pi to some even power, which is the same index here, which is what we call the weight. The square root of minus 1 here doesn't really play a role because it's always to an even power. So it just gives a negative sign, which cancels here. And so what we get is always a power of pi times some rational number. And this rational number is given explicitly. But there are good reasons why I write it like this. And this is, so this is for n bigger than or equal to 1. And this is the first example of a whole field of number theory and algebraic geometry called the special values of L functions. So this is an example of an L function, or a value of an L function. And it's related to arithmetic, number theory. And on the right-hand side, we have what is called a period, which we'll look at next time. And it involves the circumference of the circle, something geometric here. So something arithmetic, something geometric. This is a very big theme. And very active at the moment. So obviously, we understand half of the zeta values, and the question is, a question which I think troubled Euler for many years, is what can we say about the odd zeta values? So an obvious guess is that zeta 3 should be pi cubed times some rational number. That's the obvious generalization of this pattern. And the embarrassing answer to this is we don't know. We still don't know. Even today. So I will tell you, in fact, everything that we know about this problem on this board. Can I flip this? No. That's a shame. That's okay. That's not a problem. So I can give you the full history of this, everything we know about this problem. It fits on one board, hopefully. So in 1761, an English mathematician, Lambert, proved that pi is irrational. Pi is not in Q. 1882, Lindemann proved that pi is transcendental. And even today, this is a tricky result. You have to use a lot of technique to prove this result. So what transcendental means is that pi satisfies no algebraic equation. So more precisely, if p of pi equals 0 is a polynomial equation for pi, then p has to be identically 0. So there's no algebraic equation which pi satisfies. And that means that all these even zeta values, by Euler's formula, are transcendental numbers. So we know everything about exactly half of the zeta values. Then we had to wait nearly 100 years for a huge breakthrough by Apery, who was, I think, 64, or in his 60s when he proved this. He was, I think, a schoolmaster at the time. And he amazingly proved that zeta 3 is irrational. And I'll explain roughly how he did this. In 2000, Bohr and Riemann showed that infinitely many of the odd zeta values are irrational. So that's everything that's known, essentially. And the conjecture, which is completely open, very difficult, is that pi, zeta 3, zeta 5, zeta 7 are algebraically independent. Over Q. That means that there is no polynomial equation involving these numbers, which is non-trivial. There's no algebraic relation between these numbers. So what it means is that the even zeta values all reduce to pi in some sense by this formula, but each odd zeta value is like a completely new quantity, a new number. Okay, so it is not known if not known if zeta 5 is irrational. This is completely open and has been open for 50 or so years. People have tried to prove this. And it is not known if zeta 3 over pi cubed is in Q. So this is what you'd expect. You'd expect that zeta 3 is proportional to pi cubed times a rational number. Even this is not known. And we expect it not to be in Q. Even this, there's no reasonable technique yet for proving such a thing. Right, so now let me explain how one can try to prove results of this kind. Sorry? Oh, the other one, thanks. Oh yeah, thank you. So there's essentially one very simple idea which goes into proving that a number is irrational. So the question is as follows. Suppose we are given a number psi, a real number, and we think it's irrational. How do we prove it is irrational? And as I said, there's only one idea, and that is that rational numbers are repulsive. Now, I don't mean repulsive as in that they are disgusting. It means that they repel each other. They don't like to be close to each other. Okay? So what that means is they cannot be too close. So that seems like a very stupid thing to say. It's paradoxical because rational numbers can, of course, be arbitrarily close. But what this means more precisely is that if we have two rational numbers, so if we have 4 integers, and then Q1 then so I take two rational numbers, P1 over Q1, and another rational number, P2 over Q2. And if I look at the difference between them, then obviously that's P1 Q2 minus P2 Q1 over Q1 Q2. Okay, but if these rational numbers are distinct, okay, so they can be equal, this thing can vanish, but if they're distinct, then they are far apart. That's what it means to be repulsive. They repel each other. And more precisely, P1 over Q1 minus P2 over Q2 is bigger than well, it's equal to, sorry, which is bigger than or equal to 1 over Q1, Q2. So the reason for this, and this is, it's always the same fact that's used in these types of proofs, is that this quantity here is an integer, and an integer which is non-zero, because if it was 0, then these rational numbers would be equal. And so it's an integer which is non-zero, that's positive. It must be at least 1. Okay, so we'll see that again in a minute.
You assume they are co-prime, Pi and Qi.
Do I assume they are co-prime? No, I don't think so. No, I don't think so. Okay, so that's the philosophical idea that's behind a huge amount of transcendental number theory. And as I said, it uses the fact that there's no positive integer less than 1. Okay, so let's see how this works. So we, in order to prove a number is irrational, we can come up with a criterion. which is construct very good rational approximations. So if we have, if we imagine that this was, we put psi here, then if we had rational numbers such that this difference is very, very small, then this would be violated, and so psi could not be rational. That's the idea. So more precisely, here's a proposition. Suppose there exists a sequence, an infinite sequence, Pn Qn of integers, such that 1 psi minus Pn over Qn is very small. So Pn and Qn, Pn divided by Qn is a rational number that will approximate our real number psi, and it will approximate it exponentially fast. So let's say for all n sufficiently large, and where epsilon is some small number, so bigger than 1. So we're going to give ourselves an infinite sequence of rational numbers getting very, very close, very fast to psi. And so that's easy to do. Now let's make a constraint on this. So we have to control the denominators. So we want that the absolute value of Qn is going to grow exponentially, so d to the power n, for n sufficiently large. So that's very easy to achieve. So far we've really not done anything, because we can very easily fulfill these conditions always. But the tricky part is that we want to connect the denominators to the quality of the approximation, and that's that we want d times epsilon less than 1. So if these three conditions hold, then psi is irrational. It's a very, very simple criterion. In practice, it's very difficult to fulfill these three conditions. It looks easy, but it's not. So let me prove this quickly first. Suppose by contradiction the psi in fact is rational. So psi is rational. And let's assume b is positive. So let's put that into condition 1. So this implies that 0 is less than a over b minus Pn over Qn. It's less than epsilon n for all n sufficiently large. And to this equation we can multiply through by b and Qn. So I multiply through by b and Qn, we're going to get Qn A minus B Pn is less than B mod Qn epsilon Tn for all n sufficiently large. So B is positive here. Now, by the second assumption, this is less than B d to the n epsilon to the n, which is equal to B d epsilon to the n. So this is by 2. And finally, by the third condition, d epsilon is less than 1. This tends to 0 by 3. In fact, exponentially fast. So d epsilon is a number less than 1. It goes to 0 exponentially fast. Eventually, it's smaller than 1 over b. So at some point, this will be less than 1 for all sufficiently large n. But this is the point, that this is an integer so an qna minus b pn is in z. So eventually it's less than 1. It's all n bigger than or equal to some big N. And so we get an integer here which is strictly bigger than 0 and strictly less than 1. There is no such integer between 0 and 1. Contradiction. So some people say that essentially this is the only idea, or the main idea in transcendence theory, that we always somehow use this fact, that there is no integer between 0 and 1. Maybe that's a bit strong. But there's some truth in that. And I think it's fair to say that all the proofs of irrationality use this criterion in some sense because they involve constructing rational approximations to numbers. And you may think, wait a second, that's not true. Because as a student, you learn that how to prove that the square root of 2 is irrational. And it uses a different argument. It uses some proof by contradiction, some infinite divisibility. And in fact, the proof is in Plato's Theaetetus, where he explains a perfectly good proof of the irrationality of the square root of 2. But let me tell you why secretly this is the same, this technique is hiding behind the scenes, and in fact can be used to give a very good proof of the irrationality of the square root of 2. So we should start with this, which is historically the first ever number known to be a square root of 2. Not many people know this, in fact. So let's define numbers a and bn as follows. So what we can do is write square root of 2 minus 1 to the n. So recall, square root of 2 is about 1.41 something, I think. So we're going to look at square root of 2 minus 1 to the power n. And we can always write this as an integer times the square root of 2 plus, I'm going to put, sorry, actually it should be minus. Let's do that. Yep. Minus bn. Okay, so if you work this out, you get, for n equals 1, you get square root 2 minus 1. Then you get 3 minus 2 square root of 2. And you get minus 7 plus 5 square root of 2. You get 17 minus 12 square root of 2, etc. You can write down closed formulae for an and bn. And so we get a sequence where an is 1, minus 2, 5, minus 12, etc. And bn is 1, minus 3, 7, minus 17. We get two sequences of numbers. Okay, so the next observation is that the square root of 2 plus 1 times the square root of 2 minus 1 is 1. Okay, so this is what's called a norm equation. And that means if we put epsilon, our epsilon in our criterion will be the square root of 2 minus 1, which is 1 over the square root of 2 plus 1, and that's approximately 0.414, which is nice and small. So this tells us that this quantity here is going to 0 very, very fast, exponentially fast. It's like 0.4 to the n. And so this is a what's called a linear form in 1 and square root of 2. It's a linear combination of 1 and square root of 2, is going to 0 very, very fast, exponentially fast. So it gives us approximations to square root of 2. Now, an and bn are integers in this case. And so the denominator in the criterion is just 1. So that was in 2, we had a denominator of our approximation. So this was part 1 of the criterion. And part 3 was we had to check some inequality that d times epsilon is less than 1. And that's very easy because d times epsilon is about 0.4, which is certainly less than 1. And so the criterion, the proposition, implies that square root of 2 is irrational.
Then you have to divide by an, and then an can be the denominator. Why can they be?
No, so the criterion, yes, you're right. So the criterion, did I mess up? No, the criterion only.
It does not fit with.
Sorry, yes. Ooh.
You can just do it along the same line.
Yeah, you're right. You're absolutely right. I've said something wrong. But an is an integer, so you're quite right. So an, what this says is that root 2 minus bn over an. Since an is an integer, it's less than. Since n is an integer bigger than 1, this is less than epsilon in each case. Yeah, thank you. Sorry. And indeed, these quantities, bn over an, give us extremely good approximations to the square root of 2. They are, so bn over an are, what are they? 1, 3 over 2, what did I say? 7 over 5, 17 over 12, etc. And so these rational numbers converge very, very quickly to the square root of 2. Good. Okay, so that's the square root of 2, and you can do this for any.
The question was about d equal 1. Seems.
No, the question was that the denominator was the denominator of qn. So in this, qn is an, it's an integer. The denominator is 1. And if you think back to the criterion, d was the denominator, or was, oh shit, sorry. Oh, that's funny. I thought I prepared this.
You should just repeat the part of the proof of that proposition, but without D.
So say that again?
You can just repeat the proof of that proposition.
Yeah, I think it works fine. Just repeat this, exactly.
We cannot do that without D, because we need the correspondence between AM and epsilon in any case.
Let's not divide by AN. Let's just do the estimate without division.
I think it works. Yeah, sorry.
Suppose that the square root of 2 is rational.
Yeah, we've gone straight to this part, so forget this part. We go straight to this line, it works. So here we have 0 less than an root 2 minus bn. And if root 2, sorry, my notations are not great, but if root 2 were, so this is less than epsilon to the n. So if root 2 were rational, let's say call this, let's say a equals a over b, then we get 0 less than an a minus bn. B is less than b epsilon to the n. So this is an integer, and this is going to 0. Sorry, yeah. Okay, so it turns out that the claim is that you can do this for all algebraic numbers, which is a great exercise. So this is completely non-standard. I've not actually seen this written anywhere. So it's not very well known. But it goes to show that the general principle, if you do it correctly, even applies for algebraic numbers. So the next more interesting example is to do log 2. So very quickly we'll run out of numbers for which we can do this. So log 2 is not algebraic. So this is known, but here's an elementary proof that it's irrational. And it's the prototype for zeta values. So this is, so if you want, this is log 2, 2, so the first observation that if n is not equal to -1, then we can always integrate x to the n dx. That's because this is x to the n plus 1 over n plus 1 between 1 and 2. And this is some number. It's some integer with a denominator which is 1 over n plus 1. And so in particular, we can integrate any linear combination of powers of x, provided that the power is not -1. We can always integrate to give a rational number with a control in the denominator. So then the clever idea is to do the following, is to consider in is integral from 1 to 2 x minus 1, 2 minus x over x to the n dx over x. Okay, so I don't have, oh maybe I do have a cutter, cool. That's better. So if you multiply this out, the highest power will be x to the 2n, so there'll be something times x to the n plus dot 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 plus something x to the minus n. So it's a linear combination of integrals of this type. And so by using this and this identity, we get that it's an log 2 plus bn. And more precisely, an is the coefficient of, if you think about it, the only term that contributes to the log is the constant term of this polynomial. So it's the coefficient of x to the n in x minus 1, 2 minus x to the n. And by the binomial formula, you can compute this. It's some integer. So an is some integer, and bn is a rational number. But by this argument, it's going to be a sum of integrals of all these other terms, each of which has denominator given by this. So it has denominator not much space, let me write it here. The least common multiple, let's say dn, which is the least common multiple of the numbers 1, 2, up to n. I think that's right. Yeah, I was just checking that before, and I think it's actually not plus 1 because if you careful. First I wrote n plus 1 in my notes, and then just before I was just having a look. I think it's n. But it's not important. It makes no difference to the argument. Sorry?
We also have negative powers.
Yeah, so for the positive power you've got, okay, let's do it. X to the 2n minus n, so that's n. You lose 1 here, so that's n. And for the negative power, n is negative, so n plus 1 is smaller in absolute value. So you just have to sit down and check it. I think it's okay. That's the sort of calculation one never wants to have to do on the blackboard in front of people. Okay, so I should hurry up a little bit. So the fact, so I can give a very quick sketch afterwards if there's time, that dn is approximately, so I'll be sloppy about asymptotics, but it's approximately e to the n. And this uses the prime number theorem. But there are elementary proofs, very slightly weaker versions of this. I don't want to discuss this too much, but I can give a very quick sketch of why this is true. So dn grows approximately like exponential to the n. And one can be more precise about the error terms, but it's not important for us. So then let's see how small. So we have a control on the denominator. Let's see how small the integral is. So f equals x minus 1, 2 minus x over x is maximized when x is the square root of 2 on the interval x is in 1, 2. So you can check this maximum just by computing the derivative of f. And at this maximum, the value is f of root 2, which is 3 minus 2 square root of 2 equals 0.171. So you start to see these proofs require lots of miraculous identities. It's hard to see why things are going to work. So in concretely is, the first one is log 2. The second one is 3 log 2 minus 2. The next one is 13 log 2 minus 9, etc. And the absolute value of the integral is at most the absolute value of f of x, because dx over x is positive measure on the interval 1 to 2. And so this is at most epsilon to the n. So let's call this epsilon. So where epsilon is this maximum. So these integrals are getting very small exponentially fast.
F to the power n.
Oh, so thank you very much. Fx to the power n. Thank you. So they're little things to check, but I leave them as exercises. There's essentially all is in an undergraduate mathematics course. And so finally we check that dn, so the denominator d epsilon, so d, the denominator was exponential with e to the n, so d is e. We can take d equals e. So d epsilon is e times 3 minus 2 square root 2. And this is where you have to hold your breath and pray that something nice happens. And you work out that this is 0.466, which is less than 1. And there you prove that log 2 is irrational. And now you start to see why these proofs are so difficult, because it's very easy in general to construct very good approximations, but it's very difficult to construct approximations with small denominators such that this miracle occurs. So what's the general construction? So I'll explain how to do zeta 2 and zeta 3. So in general, consider a family of integrals of the form integral over sigma of f to the n omega. So sigma typically will be some region in d-dimensional real space. It's the domain of integration. Omega is a differential D form. Typically will be algebraic in some sense. And we're going to take f will be a rational function. And it's nice to ensure that f vanishes on the boundary. You don't have to have this, but this makes life better. Because if f vanishes on the boundary, typically it means that f is small on sigma, and so f to the n is very small. And that's going to make these integrals go very, very small, very fast to as n goes to infinity. So that's the general shape of these proofs. And let me quickly give you the examples for Apery theorem. So it turns out that looking at these sorts of integrals is very interesting because they carry a huge amount of zeta 2 plus Cn. And the problem is, so if you run the proof, you can run the same proof, what you will conclude is that that they cannot all be rational. So you will deduce that one of these numbers is irrational, but we already know that. We already know that zeta 2 is irrational. So if n equals 5, you get lots of different possibilities. There's one particular choice of permutation that gives an zeta 5 plus bn zeta 3 plus Cn. In general, you have zeta 2 and zeta 4 as well. It's quite complicated. And then if you run the proof in this case, you deduce that one of zeta 3 and zeta 5 is irrational. But because we already know that zeta 3 is irrational, we learn nothing. And so this is the problem. But if you do push this method, you can prove that zeta 2 is transcendental.
Are different, yes.
Oh, sorry, yeah, thank you. And
the left one corresponds to
the number of the dimension, yeah, sorry. Let's just say dim, thank you very much, that was bad of me. Dim is 5. So what you can do is generalize this to get series with just even, zeta even, and in fact you can prove using this that zeta 2 is transcendental, in fact. So that's the best you can do. And if you generalize this family, you can get linear forms in all the odd zeta values. And there's a stronger version of the criterion I didn't explain, which says that you can sometimes deduce that the vector space spanned by these numbers grows. But it's a very weak bound. But this you can, using this more sophisticated criterion, you can show that infinitely many odd zetas are irrational. So in fact, you're right. So this single geometric idea explains every single result that I explained at the beginning. But we're kind of stuck because we don't know. What we'd like to do is somehow eliminate this number to get zeta 5. But if you do that, you make the denominator worse. So no one knows how to